So now let's start with the topic of Young's double slit experiment. In short, we call it YDSE. Thomas Young took a light source and made the light coming out of it to pass through thin slits. Because beta, the wave nature of the light becomes dominant when it passes through an opening of the order of wavelength or when it interacts with a particle having size of the order of wavelength. So he made the light coming out of this source to pass through these two ultra fine slits. The opening size is kept purposefully small so that the wave nature becomes more dominant. And we have learned from the Huygens principle, every point on a secondary wavefront acts like a secondary source. So both these points will act as secondary source and visualize as if the wave is getting created from them. And these two waves are interfering. Wherever the path difference will be 0, lambda, 2 lambda, 3 lambda, you will get constructive interference. Wherever the path difference will be lambda by 2, 3 lambda by 2, 5 lambda by 2, they will try to cancel out each other. And then we observe this interference pattern on a screen. Now when we look at the interference pattern on the screen, we find these type of bands. So there is somewhere light, somewhere dark, somewhere light, somewhere dark. Dark means black. Black means the absence of color. So wherever the waves cancel out each other destructively, you see the black color. And wherever they interfere constructively, the intensity increases and you see the bright band. So you see these type of band, bright band, dark band, bright band, dark band. And they are very close to each other. Now to understand it, let's replace this model and place another model. So now here you can see that if I visualize a light joining the source to the center of the two slits and extend that line, then the point opposite to it is the place where you have got light. Since you have got light here, this is called the central bright fringe. Why it's called the central bright fringe? Because the radiation coming out of the source passing through both the slits have to travel the same distance to reach this point of symmetry. Now since both the waves travel the same distance, at this point the path difference, the difference in the path length traveled comes out to be 0. So remember that if I extend a line joining the source to the midpoint of the slits and extend it, I get the point which is central bright. Now at central bright, the path difference is 0. Now next to central bright, we see the absence of light. It means that the waves are interfering destructively. This is called the first dark. Also this one on both the sides are called first dark. So next to central bright we get first dark. Then we again find bright spots. These are called first bright. Then we again find dark spots. These are called second dark. Then we again find bright spots. These are called second bright. Then we find dark spot and bright spot and dark spot, and they have got this name. So beta, you need to understand two things. First, that we observe a pattern on the screen. This is called fringe pattern. We get band of bright, dark, bright, dark, bright, dark fringe. Now next to every bright you get dark, next to every dark you get bright, right? And the separation between two consecutive dark is same as the separation between two consecutive bright. Now bachcho, why do we find this pattern? Because as we move on the screen at different points, there is different path difference. Central bright is the place for which both the waves coming out of both the slits have to travel same distance. But if you think of any other point on the screen, let's say some point here, the wave coming out of the first slit will have to travel less, while the wave coming out of the second slit will have to travel more. Hence there will be a path difference. If this path difference becomes equals to 0, lambda, 2 lambda, 3 lambda and so on, the waves interfere perfectly constructively and you see a bright light there. And if at this point the path difference is 1 of lambda by 2, 3 lambda by 2, 5 lambda by 2 and so on, Then at this point, the two waves reaching are out of phase and they try to cancel out each other. Hence, you see a dark spot. To understand YDSE more, the most important thing that you need to understand is the path difference at any point on the screen. So that's our next mission. Let's learn it. Path difference at any point on the screen. So beta, visualize the two slits. Okay, sir. Let's say the separation between the two slits is given by small d. And there is a screen placed at a distance capital D from the slits. Now, if you think of a line joining the source to the midpoint of S1 and S2, the place where this line will cut the screen, that is your central bright. At the position of central bright, the path difference is 0 because the wave coming out of both the slits have to travel the same distance. If they travel the same distance, then obviously the path difference is going to be 0. But we are trying to find the path difference at any random point on the screen. So let's say we need to find the path difference at this point P. So as to find the path difference at point P, what to do? So path difference is path difference. Visualize the wave coming out of both the sources, both the slits trying to reach the point P. So visualize the wave coming out of first slit trying to reach the point P. Visualize the wave coming out of second slit trying to reach the point P. Our mission is to find the path difference. First of all, tell me here which wave has to travel more to reach the point P. The wave coming out of the second slit have to travel more to reach the point P. Good. Now my question is, what is the path difference? The difference in the distance. So I will say that the path difference is simply S2P minus S1P, the path difference. If this path difference, once again repeating, if this path difference becomes equals to 0, lambda, 2 lambda, 3 lambda, the two will interfere perfectly constructively, giving you maximum possible resultant intensity. And if this path difference becomes equals to lambda by 2, 3 lambda by 2, 5 lambda by 2, the two waves try to cancel out each other. This is perfectly destructive interference, and for two waves coming out having the same intensity on the screen, the resultant intensity will be 0. Now here, bachcho, our mission is to find the path difference. To find the path difference, drop a perpendicular. If you drop a perpendicular, you can say that, okay, these two lengths are now nearly the same. The wave coming out of the second slit travels this much distance extra. And sir, how to write this distance? Look in this right angle triangle. For this right angle triangle, the hypotenuse is the separation between the slits. This angle is theta and this is the path difference. The second pulse travel this much more. So sir, how much is the path difference in terms of d and theta? You can say that the path difference is nothing but d sine theta. The path difference is nothing but d sine theta. So bachcho, now if we do a little more construction, we join the point P to the central point on the line joining the slits. If this angle is theta, this angle will also be theta. Both the angles will be same. We can say that the path difference between the interfering wave meeting at point P is nothing but delta x, and that delta x, the path difference, will be equals to d sine theta. We have learned this so many times in physics. For small value of theta, sine theta can be approximated to tan theta, and that can be approximated to theta. So in place of sine theta, if we substitute tan theta, we get delta x to be nearly equal to d tan theta, as we are doing an approximation. Now since these two theta are equal, looking into this triangle, in place of tan theta, we can substitute y by d. So you can say that the path difference equals to y by d into t, or d into y by d, the same result. Now beta, this is important. The path difference equals to d into y by d. So you can say that the path difference is directly proportional to y. The path difference is directly proportional to y till the time you are playing with small theta, because only for small theta you can approximate sine theta to tan theta. So till the time your theta is small, definitely not in my diagram, because if I make small theta, the diagram becomes ugly. So the path difference is directly proportional to y. So as you keep on moving up from the central bright, the path difference keeps on increasing. We know that at the position of central bright, the path difference is 0. If you start from central bright where the path difference is 0, both the waves have to travel the same distance to reach the central bright. And as you keep on going up, the y keeps on increasing, and as the y keeps on increasing, the path difference keeps on increasing. Now visualize that the path difference initially is 0 and it keeps on increasing. So somewhere it will become lambda by 2. Where the path difference becomes lambda by 2, the waves will try to cancel out each other and you will see dark. You keep on going up, the path difference keeps on increases. Somewhere the path difference will become equals to lambda. When the path difference becomes lambda, now the waves are in the same phase, they add up and the resultant intensity is high. You see a bright spot. You keep on going up, after lambda you get 3 lambda by 2. Again the two waves try to cancel out, so you get dark. You keep on going up, the path difference keeps on increasing. At some point you will find the path difference to be 2 lambda. Path difference continuously increases as y increases. Where you get 2 lambda, again the two waves will try to add up to each other and the resultant intensity will be higher. You will see a bright spot. So what we see is bright, dark, bright, dark, bright. We need to understand that here y is the position of the point P from the center maximum. So as you keep on going away, y keeps on increasing. As the y keeps on increasing, the path difference keeps on increasing. And I tell students, this is the one thing that they should know by heart. The path difference equals to d into y by d. Now bacho, moving on. For maxima at this point, if you want P to be bright, then the path difference has to be 0, lambda, 2 lambda, 3 lambda, 4 lambda and so on. So the path difference has to be n lambda. If you want here this point P to be dark, then the path difference has to be lambda by 2, 3 lambda by 2, 5 lambda by 2. You must remember all these things. Now bacho, here for maxima at P, the path difference has to be n lambda, where n can be 0, 1, 2, 3 and so on. Now let's move on and see some points about Young's double slit experiment. So the first point goes like, the central fringe is bright because at central fringe position, we get that the phase difference is 0 because the path difference is 0. And we know that the path difference upon maximum path difference in one cycle equals to the phase difference upon maximum phase change in one cycle. As at the position of central bright, the path difference is 0, the phase difference is also 0. And as the phase difference is 0, the two vectors on the phasor diagram will add up to increase the intensity. So at the position of central bright, remember that the phase difference is 0, the path difference is 0. Next point, the fringe pattern obtained due to slit is more bright than due to a point. If rather than making slits on the cardboard sheet, if we take the cardboard sheet and make 2 holes on it, then definitely through 2 holes lesser amount of light will enter. If lesser amount of light will enter, the interference pattern won't be that bright to be observed. So that's why the fringe pattern obtained due to slits is more bright than due to if you make pinhole on the cardboard sheet. The third point, if the slit width are unequal, the minima will not be completely dark. We know that if you have got two waves having intensity I1 and I2, then the minimum possible resultant intensity is nothing but root I1 minus root I2 whole square, right? You will get the resultant intensity to be 0, pitch dark, perfect dark, only when both the sources will have the same intensity at the point of interference. If they will have different intensity, no matter which one is bigger, I1 is bigger or I2 is bigger, you are going to get some light at that point of perfectly destructive interference. So as to see complete dark, 0 resultant intensity, this is a precursor that both the sources should have the same intensity at the point of interference. So if the slit widths are unequal, the minima will not be completely dark. Second beta, for very large width, uniform illumination occurs. Means if you keep the slit width very large, you do not see any pattern on the screen. There is no bright, dark, bright, dark, bright, dark. You see uniform illumination. Why? Because you can't observe the wave pattern in its dominance, because now the opening size is way greater than the wavelength. Next point, if one slit is illuminated with red light and other slit is illuminated with blue light, no interference pattern is observed on screen. Obviously, red light and blue light have got different frequency. As they have different frequency, they will have different angular frequency. So their rate of change of phase angles will be different, and as their rate of change of phase angles will be different, they can't have a constant phase difference. And since they can't have a constant phase difference, it won't give rise to an observable interference pattern. So if you have got two different color light coming out of both the slits, then you are not going to see any interference pattern at all. Now beta, important points more that you should know. The first, if the slits are vertical, the path difference is given by d sine theta. So as theta increases, the path difference increases. So if you have got this case where the slits are vertical, then we have learned that this path difference is nothing but d sine theta. So as theta increases, as you keep on moving away and away from the central bright, as theta increases, sine theta increases, so the path difference increases. But if you have got this case that the slits are horizontal, then now as the theta increases, as you keep on going away from the central bright, now the path difference will keep on decreasing. Why? Let's see. If I ask you for these two sources placed and we are observing the interference pattern on this screen, what is the path difference? So you will say, sir, again drop a perpendicular. So this axis distance is the path difference. And if this distance between the sources is d and the point P is such that the angle you get here is theta, you will say that the path difference is nothing but looking into this right angle triangle to be equals to d cos theta. So the path difference is d cos theta. As you keep on going away and away from the central bright, the theta keeps on increasing. As theta increases, cos theta decreases. So you will say that the path difference decreases. So if the slits are horizontal, path difference is given by d cos theta, and now when theta increases, the path difference decreases. This is one important point that you should know. Now if they ask you what is the condition to see a bright spot at P, so you will say the path difference d cos theta should be equal to n lambda, 0, lambda, 2 lambda, 3 lambda and so on. If they ask you what is the condition to see a dark spot at P, so you will say that the path difference d cos theta should be equal to lambda by 2 or 3 lambda by 2 or 5 lambda by 2, that is odd multiple of lambda by 2. But so now we will talk more about fringe. It's a theoretical topic. All fringes are of equal width. All the fringes, dark fringe, bright fringe, dark fringe, bright fringe, they are of equal width. And the width of each fringe is beta. So what is beta? Beta is called fringe width. Fringe width. That is the separation between two consecutive dark or two consecutive bright. That is called fringe width. If you have got these two slits, yes sir, and this is the screen. Now think of a point P at a distance y from the central maximum. At this point, waves reach both from the first slit as well as second slit. Yes sir. We have learned that the path difference will be nothing but equals to d sine theta, and for a small value of theta this can be approximated to d tan theta, and you can say that the path difference can be written as d into y by t. Now if you want at point P a bright spot, you know that as the value of y increases, the path difference increases. At the position of central bright, the path difference is 0. And you even know that the path difference at a distance y from the central bright is given by d into y by t. The first spot where you find bright spot, what has to be the path difference there? Then we get bright spot when the path difference is 0, lambda, 2 lambda, 3 lambda, 4 lambda. At the position of first bright spot, after central bright, you will first get dark and then you will get first bright. At the position of first bright spot, the path difference has to be lambda. Similarly, at the position of second bright spot, you will get the path difference to be 2 lambda. At the position of third bright, you will get the path difference to be 3 lambda. Now, the gap between two successive brights or two successive dark is called fringe width. Now, what will be this distance? Sir, easy to find. How? Substituting here the path difference equals to lambda, you can find y. You will say that lambda equals to d into y by d. So the place at which the path difference is lambda, for that place the distance from central bright has to be d into lambda by d. So if you start from the central bright, at central bright the path difference is 0. The first bright will be at a distance beta. The second bright will be at a distance 2 beta. The third bright will be at distance 3 beta. Fourth bright at distance 4 beta from the central bright, where beta is nothing but lambda d by d. This is called the fringe width. So width of each fringe is beta, where beta equals to lambda d by d. This is something you have to remember. The fringe width observed in the Young's double slit experiment equals to wavelength of the light used multiplied by separation between the slits and the screen upon the separation between the slits. And the angular fringe width theta. So what is the meaning of angular fringe width? Angular fringe width is the angle subtended by a fringe width on the slit side. For example, here you have got this central bright. Okay, the first bright will be at how much distance from the central bright? So that is called fringe width. That is what we found to be equal to lambda d by d. Now question is, what will be the angle subtended by this length equals to fringe width on the slit side? So sir, let's say that angle is theta. The distance between the slit and the screen is capital T. So you can say theta equals to beta by d, and that will be equals to lambda d by d upon d, and that will be nothing but lambda by d. So how to find angular fringe width? Think of the fringe width beta and think of the angle subtended by this length equals to fringe width on the slit side. This angle is called the angular fringe width, and this angle is nothing but beta by d. Next thing, bachcho, if the whole YDSE setup is taken into another medium, then wavelength changes, so beta changes. We know that if a ray of light moves from air, where we take the refractive index to be 1, into water, where we take the refractive index to be equals to 4 by 3. Once the ray moves from air into water, the speed becomes 3/4. The frequency remains the same and the wavelength becomes 3/4. So inside the denser medium, the wavelength decreases. If the wavelength will decrease, definitely the fringe width will decrease. If you put the entire YDSE setup inside water, then the wavelength becomes 3/4. If the wavelength will become 3/4, the fringe width will become 3/4. It means that the gap between two successive bright or two successive dark will become 3/4. So if the whole YDSE setup is taken into medium, then wavelength changes and so does beta changes. For example, in case of water, the wavelength inside water is 3/4 of the wavelength in air. So wavelength inside water is wavelength in air upon the refractive index of water, that is 4 by 3. So you get 3 by 4 into wavelength in air. And the fringe width inside water is also equal to fringe width in air divided by the refractive index of water. As lambda becomes 3/4, the fringe width becomes 3/4. Here just substitute 4 by 3 and you will get the idea. Next, bachcho, fringe width is inversely proportional to separation between the slits. We have got that fringe width equals to lambda d by d. So fringe width is inversely proportional to separation between the slits. That is, with increase in the separation between the sources, the slits, beta decreases. So if you keep the slits really close, a small value of d, the fringe width will be high. And if you keep the separation between the slits to be high, then the fringe width will be less, keeping everything else same. Now understand that the closer the fringes you will have, the more difficult it will be to separate out between two bright fringes. Remember the first drawing which I showed you, that's an actual picture. You get bright dark, bright dark, bright dark, bright dark, and they're so close that you can't see them clearly. So if bachcho D increases, the separation between the slits is increased, beta decreases, the separation between two successive bright decreases, and when the separation between two successive bright decreases, it becomes difficult to observe the interference pattern. If they get, let's say, too close, too close, too close, you will see it as a continuous illumination. Next point, bachcho. Position of nth bright fringe from the central maxima will be where? So you will say, sir, there is central maxima. The first bright is at distance beta, second bright at distance 2 beta, third bright at distance 3 beta, fourth bright at distance 4 beta. So the position of nth bright from central maxima will be nothing but n beta. So easy to remember. Next, where n is nothing but 0, 1, 2, 3. Position of nth dark fringe from the central maxima. We know that between two consecutive bright we will get dark. So we get first bright at a distance beta. So we will get first dark at a distance of beta by 2. So do remember this. You have got central bright, the first dark at distance of beta by 2, the second dark at distance of 3 beta by 2. Do notice that the gap between two consecutive dark is still beta. So you get first dark at beta by 2, second dark at 3 beta by 2, third dark at 5 beta by 2, fourth dark at 7 beta by 2, and so on. So the position of nth dark is nothing but 2n minus 1, and this quantity is beta by 2. 2n minus 1 beta by 2. So for first dark you will substitute here 1, you will get 2 minus 1 into beta by 2, that gives you beta by 2. For second dark you will substitute here 2, you will get 3 beta by 2. So position of nth dark is nothing but 2n minus 1 into beta by 2, where n equals to 1, 2, 3, and so on. So now doing the last point. In YDSE, if n1 fringes are visible in a field of view with light of wavelength lambda 1, while n2 with light of wavelength lambda 2 in the same field of view, then what is the correlation between n1 lambda 1 and 2 lambda 2? So let's think we are looking at a certain length, let's say y of the screen. When we use a source of wavelength lambda 1, then we are able to see here n1 fringes. So we can say that n1 into beta 1 equals to y. If on using another source of wavelength lambda 2, you see here in the same length, in the same field of view, n2 fringes, then you will say that n2 into beta 2 also equals to y. So we can say that n1 beta 1 equals to n2 beta 2. In place of beta 1, you can write lambda 1 d by d. In place of beta 2, you can write lambda 2 d by d. So cancel out this capital D and small d. The condition comes out to be n1 lambda 1 equals to n2 lambda 2. So remember this particular condition. So now talking about few more important points. So condition for observing sustained interference. The first point is the initial phase difference between the interfering waves must remain constant. So as to observe sustained interference pattern, the phase difference should be constant. It means that the sources should be coherent. Otherwise, the interference will not be sustained. You won't be able to observe it. Second, the frequency and the wavelength of the two waves should be equal. Isn't it obvious? For the sources to be coherent, for the phase difference to be constant, the sources must have same frequency. And since we have got light interfering here, if the frequency has to be same, the wavelength also have to be same. If not, the phase difference will not remain constant, and so the interference will not be sustained. So I think that you already knew this point 1 and point 2. The third point. The light must be monochromatic. If rather than using monochromatic light, you use light of two different colors, then you won't be able to observe the interference pattern. So this eliminates overlapping of pattern as each wavelength corresponds to one interference pattern. These type of questions are asked. If you make white light pass, you place a source of white light and make white light pass through the two slits. What will happen? Now white light is a mixture of all the 7 colors. This central point will be the central bright for all the colors. And since all the colors, whether red, whether violet, whether indigo, all the colors will show here constructive interference. They will be bright here, and when all the colors will be bright, you will say that the color here will be white. But we know that the lambda of red is greater than the lambda for violet. Since the wavelength of red light is greater, we know that the fringe width for red will be greater than the fringe width for violet. So at different places you will find the bright of violet and the bright of red, right? So you won't be able to observe the interference pattern properly. So that's why to observe the interference pattern, it is said that it is better to use monochromatic light so that the interference pattern of two different colors do not overlap over each other. The next point, the amplitude of the waves must be equal. Sir, why are you saying that amplitude of the wave must be equal? The beauty of interference is not that light plus light is more light. The beauty of interference is that light plus light becomes darkness. And for two waves to completely cancel out each other, they should have equal amplitude. When I say equal amplitude, equal intensity. And they should have a phase difference at the point of interference equal to pi, 3 pi, 5 pi, 7 pi, 9 pi. So if you want to observe sustained interference and if you want to observe it clearly, then it is recommended that the amplitude of the waves must be equal. This improves contrast. With I max, the maximum possible resultant intensity equals to 4I0, 4 times that of individual, and I minimum equals to 0. So your bright are quite bright and your dark is completely dark. So you will be able to see the interference pattern better. Moving on, the source must be close to each other. So why the source must be close to each other? We know that the fringe width equals to lambda d by t. If we keep the slits far away, the d will be greater, then the fringe width will be less. If the fringe width will be less, in a given length of screen you will get more number of bright fringe. But if all the bright fringe come very close, you won't be able to observe them as distinct fringes. It will appear as an overlap. So beta, to observe the fringes clearly, the separation between the slits should be small. If d will be small, then the fringe width will be large, and when the fringe width will be large, you will be able to see clearly bright, then a dark, then again bright, then again dark, because the gap between two successive bright will be more. So the source must be close to each other. Otherwise, due to small fringe width, as the fringe width is inversely proportional to separation between the slits. Otherwise, due to small fringe width, the eye cannot resolve fringes, resulting in uniform illumination. That's why beta, d should be small. Now we will talk about something, shifting of fringe pattern in YDSE. Why are we talking on this? Which topic we are going to cover here? Let's see. Sometimes you will find questions like, in front of one of the slits we have placed a transparent material, and due to this transparent material the fringe pattern shifts. The first question is, why does the fringe pattern shift? Because when a light ray travels a distance t in a medium of refractive index mu, it is as good as traveling a distance mu t in vacuum. Now this distance mu t is called optical path length. This distance mu t is called optical path length. For the sake of understanding, let's take an example. Think of two light rays, one moving in vacuum and one moving inside glass. And let's say both of these light rays cover the same distance t. We know that in vacuum the speed of light is c. The first light ray crosses a distance t in vacuum. If it crosses a distance t in vacuum, it will take a time to cross. The time taken to cross will be equals to t by c, the distance traveled upon speed. Now let's take another case of a light ray entering into glass. We know that the refractive index of glass is 3 by 2. So as soon as this light ray enters inside the glass, its speed will become 2/3. So the speed will be 2c by 3. So the time taken by this light to cross this glass will be its thickness upon the speed 2c by 3, that gives you 3t by 2c. So do understand that since the glass has refractive index of 3 by 2, the time taken to cross the same thickness of glass is 3 by 2. When a light ray goes from one medium to another, what happens to the frequency? What's it? When light goes from one medium to another, what happens to the frequency? Remains the same. Speed changes, wavelength changes, frequency remains the same. When light goes from one medium to another medium, the frequency remains the same. If I ask you what happens to angular frequency, then the frequency remains the same, angular frequency remains the same. And what exactly is angular frequency? The angular frequency is the rate of change of phase angle with respect to time. Now, whether the light travels in vacuum or whether the light travels inside glass, it has the same frequency, it has the same angular frequency, so it has the same rate of change of phase angle with respect to time. But when light travels inside glass, it takes more time to cross. Since it takes more time to cross, the phase change with the same angular frequency will be 3 by 2 times. So if here a phase change of delta phi takes place, that will be equals to omega into the time taken, that will be omega into t by c. For this light ray traveling a distance t inside glass, the phase change will be equals to omega into the time taken to cross, and that time taken to cross will be 3 by 2 t by c. So the phase change will be 3 by 2 times compared to the same distance traveled in vacuum. And we know that the phase difference and the path difference are directly proportional. The phase difference upon maximum phase change in one cycle equals to path difference upon maximum path difference in one cycle, lambda. So when the light travels inside glass, the omega, the rate of change of phase angle, remains same, the time increases. So by the time the light crosses glass, since it has spent more time, the phase has changed by more amount and the effective path length is greater. We call this effective path length as optical path length. So just remember now, traveling a distance t in vacuum, whatever phase changes takes place, traveling the same distance t inside a medium of refractive index 3 by 2, the phase change is 3 by 2 times the phase change in vacuum. So if a light ray travels a distance t inside a medium of refractive index mu, it is as good as the light travels a distance mu t in vacuum, and this distance mu t is called optical path length. Optical path length. So if tomorrow you have a slab of thickness 2 centimeter, and let's say this slab is made up of some special material having refractive index 2, then when a light ray travels to this slab, it is as good as traveling a distance of 4 centimeter in vacuum, mu into t. So traveling a distance of 2 centimeter inside a slab of refractive index 2 is as good as traveling a distance of 4 centimeter in vacuum. Keep this important point in mind. So this is really important point. Now beta, what happens here is, if a transparent thin film of mica or glass or something else is put in the path of one of the wave, then the whole fringe pattern gets shifted. Why? Listen to it. Now beta, let's say here you have got two slit S1, S2, and there somewhere you have the source. If let's say in front of the first slit you keep a transparent material of thickness t having refractive index mu. My simple question from you is, will you still find the central bright at the same spot? So central bright is the place where the path difference is 0. Now if we look till here, which wave has traveled more? The wave coming out of the slit 1 or the wave coming out of the slit 2? So beta, till here, the lower wave has traveled a distance t in vacuum. No doubt the upper wave has also traveled a distance t, but it has traveled a distance t inside a medium of refractive index mu. So the optical length, the length that should be considered, will be mu t. So traveling a distance t inside a medium of refractive index mu is as good as traveling a distance mu t in vacuum. So tell me, till here, whose phase has changed more? Geometrically, they have traveled the same distance, but optically, the one moving in denser medium has traveled more. Now beta, till here, the wave coming out of the upper slit has traveled more. Central bright is the place where the path difference is 0. Till this line, the upper wave has traveled more. So after this line, the second wave, the wave coming out of the second slit should travel more. So you will find the central bright somewhere here. The wave coming out of the second slit will have to travel more. How much extra? You will say that the wave coming out of the second slit will have to travel exactly more by the amount by which the wave coming out of slit 1 has already traveled more. How much more the wave coming out of slit 1 has traveled more till this place? You will say, sir, the wave coming out of slit 1 travels a distance t in a medium of refractive index mu, so it is as good as traveling mu t. While the wave coming out of the slit 2 travels a distance t. So the extra distance traveled by the wave coming out of slit 1 is mu t minus t. And that's why the central bright shifts upwards. So beta, let's say here we have got two slits S1 and S2. And in front of the upper slit, you have placed a medium of thickness t having refractive index mu. You can see in the diagram, we have shifted the central bright up here. Now, by how much distance does it shift? Let's see. If the film is put in the path of upper wave, the fringe pattern shifts upward. And if the film is put in the path of lower wave, the pattern shifts downward. Now, shifting in the fringe pattern in YDSE. So how much does it shift? Our mission is to find this distance y by which it shifts. So you can see that this medium of thickness t having refractive index mu produces a path difference between the two rays equals to mu t minus t or mu minus 1 into t. Sir, how do you get this? Think of this much part. The first wave travels in a medium of refractive index mu, a distance t, it travels mu t. The second wave travels a distance t. So the path difference has to be the distance traveled by the first wave minus the distance traveled by second wave. That will be mu t minus t or mu minus 1 into t. So the additional path difference created due to the placement of this slab is nothing but mu minus 1 into t. The first one travels mu t, second one travels t. The difference is mu minus 1 into t. Now, how much will the fringe shift? At the position of central bright, the path difference has to be 0. Let's say the central bright has shifted by some distance y upwards. So we will say that now the ray coming out of the slit 2 will have traveled same excess distance, so that here the path difference becomes 0. Due to the insertion of this slab, the first wave travel an extra distance of mu minus 1 into t. So same extra distance has to be traveled by second wave. So you will say that mu minus 1 into t, the extra distance that has to be traveled by second wave has to be equals to d sine theta, which is approximately same as t tan theta, which will be d into y by t. So you get y. The shift in the position of central bright is nothing but mu minus 1 into t into d by d. So mu minus 1 into t into d by d. Now beta, if I multiply and divide with lambda, I can write lambda d by d as beta, French width. So this can also be written as beta by lambda into mu minus 1 into t. This is not rocket science, this is an easy thing. Now but moving on. If shift is equivalent to n fringes, now one fringe is at distance beta, two fringe is at distance 2 beta, third fringe is at distance 3 beta. So n fringes are at distance of n beta. So here if you substitute n beta on the left hand side, so you will get n beta equals to beta by lambda into mu minus 1 into t. So you can cancel out beta and find that n comes out to be mu minus 1 into t by lambda. Or you can rearrange and write t equals to n lambda upon mu minus 1. Here remember that on placing a slab, the position of central bright shifts up or down depending in front of which slit you have placed the slab. But the fringe width remains the same. It means that still the separation between two consecutive bright or two consecutive dark will be beta, and that will be equals to lambda d by t. So by placing a slab in front of one of the slits, we can't change the fringe width. Now let's move on to the last illustration of this hour, and that is missing wavelength in front of one of the slits in YDSE. In previous year papers, this question has been asked many a time, so I am taking it as a independent article. So if we look at the figure, and here we have got two slits S1 and S2, and question is we need to find the missing wavelength in front of one of the slit in YDSE. So which particular wavelengths would be found at point P, which is in front of one of the slits? That's our mission to find. So sir, see, if you look at this diagram, the distance traveled by the wave coming out of S1 and reaching P will be t. The distance traveled by the wave coming out of S2 and reaching P from Pythagoras theorem will be under root of t square plus d square. So you can say that the path difference between the wave reaching at point P is nothing but S2P minus S1P. And that S2P minus S1P can be written as under root of capital D square plus small d square minus d. Now we are going to do a little bit of binomial approximation here. Rather than writing this as under root of d square plus d square, we will write it as d square plus d square raised to the power of half. And that can be thought of as d times 1 plus d square by d square raised to the power of half. Now, if you have got this, and let's say you know that d is less than d. For d less than d, d square by d square will be less than 1, and then you can do binomial approximation. Binomial approximation tells us that for x less than 1, 1 plus x raised to the power of n can be approximated to 1 plus nx. So here doing the binomial approximation. So from binomial approximation we can say that the path difference equals to d into 1 plus half times of d square by d square minus t. Now open up this bracket. What you get is d plus d square by 2d minus t, and this d get cancelled. So you get that path difference equals to d square by 2d. What are we trying to find? We are trying to find the missing wavelength in front of one of the slits in YDSE. So we wish to find which particular wavelength will be missing from here. Sir, we know that the path difference at this point is d square by 2d, given that small d is less than capital D. Now how to find which wavelengths are missing? The wavelengths that will be missing will be the one for which at this point P destructive interference takes place. For perfectly destructive interference to take place, the condition is the path difference should be equals to 2n minus 1 into lambda by 2, where you start n from 1. So for dark at P, the path difference, which is equal to d square by 2d, should also be equal to 2n minus 1 into lambda by 2, where n changes from 1, 2, 3 and so on. So you will say the missing wavelength at P are the one corresponding to which this condition is satisfied. So cancelling out 2 and 2. So you will say the wavelengths which are equals to d square upon 2n minus 1 into d. Such wavelengths will be missing. So you will say lambda has to be equals to d square upon 2n minus 1 into d. Now start substituting the value of n. By substituting the value of n equals to 1, 2 and 3, you will say that the wavelengths that are missing will be d square upon 2 into 1 minus 1 into d, that is d square by d, or d square by 3d, or d square by 5d and so on. So the missing wavelengths at this point P will be nothing but d square by capital D, d square by 3 times capital D, d square by 5 times capital D and so on. So that's all in this hour. See you guys in next hour, where we are going to talk about diffraction and polarization. See you guys in next hour. Bye bye. So that's all for now. See you guys in the next hour.